Okay, so this is the last section that we need to cover in Chapter 1, Section 1.7. What we're talking about here are some special types of matrices. All of the matrices in this section are going to be square matrices, but they're also going to have some other interesting characteristics, and we're going to kind of look into what those characteristics sort of imply about how we use those matrices. So 3 different types: diagonal matrices, triangular matrices, and symmetric. So to start with, we're going to talk about a diagonal matrix. We say that a square matrix A is diagonal if the ijth entry of A is equal to 0 anytime I is not equal to j. Now, again, if you're still getting used to this notation and thinking about what these sorts of conditions actually mean when you look at a matrix of that type, remember, if I is equal to j, then the row and column that this entry appears in are going to have the same number, 2, 2, 3, 3, so on. That would put the non-zero entries, or I shouldn't say non-zero, that would put any entry where I and j are equal to each other on the main diagonal. If I is not equal to j, then we're talking about all of the entries that are off the main diagonal somewhere. So what this is saying is that a diagonal matrix is a matrix where a square matrix where every entry that's not on the main diagonal is a 0. Now the main diagonal entries might be 0, they might not. So in this case, we have a 3 by 3 matrix where all of the main diagonal entries are non-zero, but everything else is a 0. This 4 by 4 is a diagonal matrix, and 2 of its main diagonal entries are 0, 2 of them are not. That doesn't really matter because the condition here says nothing about what's supposed to be on the main diagonal. It just says everything that's off of that should be a 0. Any 0 matrix, if it's a square matrix, is a diagonal matrix, and the identity matrix, as you can imagine, is also a diagonal matrix. Occasionally, I don't think your book uses this notation, but it's a really useful notation for diagonal matrices. We sometimes use this. Diag is short for diagonal. D1 through Dn is a way of notating this diagonal matrix, where D1 through Dn show up in that order from top left to bottom right along the main diagonal. Because we know it's a diagonal matrix, it automatically implies everything else is equal to 0. Okay, that's a common notation in other books. I just don't think our book tends to use that one. When we're working with matrix multiplication, diagonal matrices are easily the most convenient matrices to work with. And we're going to see why in a moment. See if you can confirm these properties. I'm not going to prove these to you, but it would be worth checking this on your own. The inverse of any diagonal matrix will exist if and only if the main diagonal entries are all non-zero. So for example, in my 2 examples up here, this diagonal matrix would be invertible because all of its main diagonal entries are non-zero, but this one would not be invertible because not all of its main diagonal entries are non-zero. If you remember, we showed in an example in a previous section that if a column of zeros exists in a matrix, then it's not invertible. And notice that's what happens if a diagonal matrix has a 0 somewhere off of its main, or somewhere on its main diagonal. But if a diagonal matrix has only non-zero entries on its main diagonal, then it's invertible, and its inverse looks like this. It's another diagonal matrix where each entry is just the reciprocal of the corresponding main diagonal entry from D. That's really easy to compute, just taking the reciprocal of n numbers. Exponents are also very easy to compute with diagonal matrices. If D is diagonal, whether or not there are zeros on its main diagonal, raising D to the kth power is the same thing as raising all the diagonal entries to the kth power. Now, if you remember when I talked about powers of matrices, I said don't just assume that you can just raise all of your entries to the power of whatever it is you're raising D to, k in this case. Diagonal matrices are an exception to that rule. You actually do get to do that with diagonal matrices. And again, see if you can see why this is true by playing with this idea. You know, pick a diagonal matrix and square it. Watch what happens, okay? This actually follows from a more general property of diagonal matrices. It's what happens if I multiply any diagonal matrix to any other matrix. Notice if I have a diagonal matrix here, and this is just an example pulled from your book, 3 by 3, D1 through D3, and if I want to multiply that on the right by just some general matrix, in this case a 3 by 4 matrix, then this D1 is simply going to be multiplied to each individual entry in the first row, giving me the first row of my result. And you can see that if you compute this first row. Pick up a column, drop it on this row. Everything except for this first term here is going to be multiplied to a 0. So the only thing I get in this first entry here is D1 times A1. Similarly, D1 times A12 will be this entry, and so on. Beyond that, if I want to get my second row for this product here, then I can multiply D2 by every entry in the second row of this matrix. D2 times each entry. D3 times each entry in this row gives me this row. So that's faster than having to go through the usual dot product method of finding these entries. And the reason that's so much easier is because of all these zeros. If you ever take a course called numerical analysis, you'll talk about what's called a sparse matrix. Sparse matrices are matrices that have lots of zeros in them. And for computational purposes, we like sparse matrices because there's a lot less computation to do, considering the fact that the 0 just knocks out a bunch of those terms. The zeros do that. What happens if you multiply a diagonal matrix on the right? Well, now the diagonal entries are no longer determining rows of our product, they're determining columns of our product. Notice D1 times each individual entry in this column gives me each individual entry in the result. And then D2 times these entries give me these entries. D3 times these entries give me those entries. And again, do the multiplication the long way first to see why that's happening. It should give you a feel for why these properties hold. Okay, so that's a little bit about diagonal matrices. We're going to return to those a number of times over the course. In Chapter 5 in particular, we're going to talk about how to diagonalize certain matrices. That's a ways off, though, so it's a little preview, I guess. All right, let's move on to the next type of matrix that we want to talk about, triangular matrices. So if A is a square matrix, and if Aij is equal to 0 whenever I is less than j. Notice this looks similar to the definition of a diagonal matrix, except instead of having a not equal to symbol here, I have a less than. In this case, we say that A is lower triangular. If Aij is equal to 0 whenever I is greater than j, then we say A is upper triangular. And any matrix that's either upper or lower triangular can also simply be called triangular. Why do we use this terminology, and how do you interpret this? Well, a triangular matrix is, without using this definition, we can think of a triangular matrix as any matrix that has all zeros either above its main diagonal or below its main diagonal, or both. So, for example, if you take a look at this matrix right here, this is what we would call a lower triangular matrix. Now, why is it lower? Well, first of all, notice if I go like this, if I group up all of the entries that are either on or below the main diagonal, these entries can be whatever I want them to be. Everything else is going to be zeros. So everything above the main diagonal is a 0. But the term lower triangular is supposed to refer to this triangle, which includes all of the entries that aren't necessarily 0. And let's see if we can confirm that with this definition here. Remember, we say that a square matrix is lower triangular if Aij is equal to 0 anytime I is less than j. In other words, anytime the row number is less than the column number. Well, this entry right here is my 1, 2 entry. The row number is 1, the column number is 2. Notice that the row number is less than the column number. Similarly here, this is the 1, 3 entry, and this is the 2, 3 entry. All three of these entries have a row number that's less than the column number. So what that basically means is if you have any entry whose row number is less than its column number, that would put it above the main diagonal. Similarly, if we flip that inequality and the row number is greater than the column number, that puts us below the main diagonal, giving us a matrix like this. Okay, so here we have an upper triangular matrix because those entries that are either 0 or not 0, the ones that we don't have any conditions on, are on this upper triangle. Everything below that is going to be a 0. Notice also, if a matrix is both upper triangular and lower triangular, that's the same thing as a diagonal matrix. So diagonal matrices are actually a special case of a triangular matrix. That means we're talking about a generalization. Now let's look at some theorems for triangular matrices. And we're not gonna, we have one proof here, which I'm gonna illustrate a little bit more closely with an example. But let's just kind of read through these. So if you have a lower triangular matrix, its transpose will be upper triangular, and vice versa. The transpose of an upper triangular matrix is lower triangular. And that's not hard to visualize, because remember, you can think of the transpose of a square matrix as reflecting that matrix across its main diagonal. So if I take this lower triangular matrix, all of the zeros above the main diagonal will then be below the main diagonal after taking its transpose. I think I was off the screen there. Yeah. So you can visualize these zeros being passed below the main diagonal. The product of lower triangular matrices is lower triangular, and the product of upper triangular matrices is upper triangular. And that's a very useful property. That's the one that we proved down here, and I'm going to illustrate with an example in a moment. C. A triangular matrix is invertible if and only if its diagonal entries are all non-zero. In order to prove this one, we need some properties of determinants, and we will prove it, but not until chapter 2. And finally, the inverse of an invertible lower triangular matrix, so remember, that would imply that its diagonal entries are all non-zero, but if it's invertible, then the inverse of an invertible lower triangular matrix will also be lower triangular, and the inverse of an invertible upper triangular matrix is also upper triangular. We can't prove C and D yet. A is easy enough to visualize, so let's look at proving B. Again, for this one, let's assume that we're talking about lower triangular matrices, since the case of upper triangular is going to be so similar. We'll just focus on that. So this proof is out of your book. And what they're doing is they're saying, let's let A and B both be lower triangular, and then let's pick some entry that would be above the main diagonal. We want to show that if we pick some arbitrary entry that's above the main diagonal, in the product of these two, it would have to be a 0. That would make it a lower triangular matrix. And this is where they're showing that. This is basically what results from the dot product of the jth column of B with the ith row of A. And what happens is for part of this, for the first part of the terms in this product, each one of these, of this dot product, each one of these products will have a 0 as one of their factors coming from one of your matrices. And then in the second piece right here, each of the products in this sum are also going to have a 0 in their as one of their factors coming from the other matrix, and so that this is just a sum of zeros making a 0. It's a little bit tricky to follow, especially since we haven't been using this notation when we talk about the product of matrices. So let's illustrate with an example. I'll do this here. Actually, let me see if I can squeeze this up here. So let's take a 3 by 3 lower triangular matrix. 1, 2, 3, 4, 5, 6. It doesn't really matter because I'm not going to multiply the entire thing. Okay, and then let's multiply it by another lower triangular matrix. So let's say 1, 1, 1, 2, 2, 3. Zeros elsewhere. Okay, what I want to do is show that this is lower triangular. I didn't leave myself much room here. But let's suppose that this is my main diagonal right here. So I'm going to have 3 entries up here, 1, 2, 3, and I want to show that all 3 of those have to be zeros. Why would all 3 of these need to be zeros? Well, let's think about where this entry comes from right here. This is my 1, 2 entry. It's going to come from taking the second column of this matrix and multiplying it to the first row, or taking the dot product of that column with this row. But look at what happens. The 0 that we have to have in this matrix is going to get multiplied to that 1, and the other 2 non-zero entries are going to be multiplied to these 2 entries, which have to be zeros. So each product is going to be a 0, adding up to 0. And the same thing's going to happen for this entry too. Third column times this first row, every product is going to have a 0 in it. Everything adds up to 0. So that's basically what this proof is saying in a more general way. Okay? All right. So we're not going to do much with triangular matrices right now. We'll expand on their properties as we get further in to this material, or into this course. But for now, we're going to go ahead and move on to symmetric matrices. What is a symmetric matrix? I've actually defined this already in a previous section, but I had mentioned it back then, and I had said, don't worry about that definition right now. We'll be more careful in defining it later, and now it's later. So a square matrix A is said to be symmetric if it's equal to its own transpose. Okay, so if A is equal to A transpose. What this means is if you take a square matrix, and remember its transpose looks like flipping it across its main diagonal, then you should end up with the same matrix that you started with. But that implies a kind of symmetry, hence the name, about that main diagonal, where entries here look like mirror images across that main diagonal. That's what all symmetric matrices look like. Notice diagonal matrices are also symmetric because all of the entries that are off the main diagonal are zeros. So you're just swapping zeros with zeros when you take that transpose. Okay? So these are examples of symmetric matrices. Okay. So let's talk about a theorem regarding symmetric matrices. There's 3 here to talk about, or 3 properties. If A and B are symmetric matrices with the same size, and if K is any scalar, then A transpose is also symmetric. A plus B and A minus B are also symmetric. And K, where K is a scalar, A is also symmetric. Okay? These are all very straightforward to prove, but you have to remember you're using the definition of a symmetric matrix in order to prove this, which is to say, for example, we're going to prove C here. If I want to show that KA is symmetric, then I have to prove that it's equal to its own transpose. Well, let's do that one. If A is symmetric and K is any scalar, in order to prove that KA is symmetric, I should start by taking the transpose of that matrix and see what happens. Now we know from a previous section, I think section 1.4, we showed that the transpose of a scalar times a matrix is equal to that scalar times the transpose of the matrix A in this case. But we assumed that A was symmetric, which means A transpose is just equal to A. Now notice what happened. KA, when I took its transpose, resulted in KA, the same matrix. That means KA is symmetric by definition. Okay? The other 2 properties are just as easy to prove. You just have to remember to use those properties of transposes that we already talked about. Okay, a couple more theorems here, and then I believe, then we're done. So this one, if A is an invertible symmetric matrix, then A inverse is also symmetric. And this is an interesting property. In order to show this, remember, we have to show that the transpose of A inverse is equal to A inverse, right? We're showing that this when you take its transpose is equal to what you started with. So let's do that. Let's suppose A is invertible and symmetric. Well, if I were to take the transpose of A inverse, which exists because A is invertible, we have a theorem that we proved a while back that says that the transpose of the inverse of a matrix is equal to the inverse of the transpose of A in this case. Now we use the assumption that we made here. A is symmetric. If A is symmetric, then A transpose is the same thing as A. And so I'm left with A inverse here. Notice A inverse, its transpose is equal to A inverse. That's the defining property of a symmetric matrix. The transpose is equal to itself. Okay? So another one in the bag. Let's get this last theorem down, and then we'll be able to wrap this up. Now this is the theorem that I had mentioned earlier on when we first defined transposes and matrix multiplication. We did an example where I had a matrix A, and we took the trace of A transpose times A. And in the process of doing that example, I had mentioned that after multiplying A transpose times A, we had gotten a symmetric matrix. I think that's the time when I first introduced that term. I said, look at this matrix, it's interesting. It has this sort of symmetry about the main diagonal. And then I had alluded to the fact that that will always be the case for any matrix A. Even if A is not square, it just needs to be an m by n matrix. So how can we prove that that will always happen? In other words, if A is an m by n matrix, how do we prove that A transpose times A and, in fact, A times A transpose are both symmetric matrices? So let's do that down here. We're going to assume A is an m by n matrix, does not have to be square. The transpose of A would be an n by m matrix. So A transpose times A is an n by m times an m by n, and so the result would be n by n. Notice, even though A was not square, A transpose times A is square. It's an n by n matrix. So that means it can possibly be a symmetric matrix. But then to confirm, I need to show that if I take the transpose of this guy, the transpose of A transpose times A, it should give me the same thing that I started with. So we do that here. What is the transpose of A transpose A? Well, remember, if we take the transpose of a product, we can reverse the order of these two matrices and take their transposes. We showed in a theorem that that would be the case. So this A is going to come over here, and then I take its transpose. This A transpose is going to move over here, and then we take its transpose. But what is A transpose transpose? Well, remember, if you take a transpose of a matrix twice, you get back to the original matrix. So this becomes A transpose A. And notice we have the same thing here that we were taking the transpose of over here, meaning this guy is symmetric. Okay? Proving the other case that we mentioned in this theorem, that A transpose is symmetric, follows essentially the exact same steps. So we're not going to go through that here. This is an important property. We're not going to be using it a whole lot in this class, but in a second course in linear algebra, especially if you're studying singular values and singular value decompositions, this property is important there. But we're going to go ahead and leave off with that, and that's going to wrap up chapter 1 for us as well.